Swayam Prabha. Digital India. Educated India.
So, goodness of fit measure. Suppose this is your x and this is your y and this is basically your y bar and this is the line that you have fitted. This is the SRF, which is yi equals to alpha hat plus beta hat xi. Now, you take any value of x, let us say this is your x value. So, obviously, you will get an observed y, that is called yi, this is xi, right, observed. So, that means, and your line says this should be your predicted consumption, which let us say that I am denoting by yi hat. Okay. So, that means what is this yi minus y bar? This is called yi minus y bar. Now, if you recall what I said just before sometimes back, that the entire purpose of econometric analysis to explain the variation in y, and what is the variation in y? That is yi minus y bar around its mean value, that is the variation. If you take summation and square it up, then it is known as total sum of square. I will write here. So, summation yi minus y bar whole square I running from 1 to n is called total sum of square or TSS. Now, out of this total variation in y, which is given by summation yi minus y bar whole square, how much your model is able to explain? Your model is able to explain only this part yi hat minus y bar. Okay? So, yi hat minus y bar, and how will you denote that? This is yi hat minus y bar, this much you have explained, and let us again take the summation and square it up. Okay? So, that means summation yi hat minus y bar whole square I running from 1 to n is actually called explained sum of square, because that is what you have explained, explained sum of square or ESS, explained sum of square or ESS. And what is pending, what is remaining that you are not able to explain is here. Sorry, this is called TSS and this is called yi hat minus y bar, again you take square, and that is called summation yi hat minus y bar, that much you have explained I running from 1 to n, that is called explained sum of square, explained sum of square or ESS. and then this is the portion that you are not able to explain, that is called yi minus yi hat, okay, yi minus yi hat and take square. That is the portion that you are not able to explain. So, this is called yi minus yi hat square and I running from 1 to n, then this is called residual sum of square. So, that means this much you are not able to explain, residual sum of square or RSS. All right. So, that means from this we got TSS, we got ESS, we got RSS, and the diagram easily shows the TSS, this entire portion yi minus y bar is actually a summation of two components. So, from the diagram I can easily write that TSS equals to ESS plus RSS. This is one important relationship, TSS equals to ESS plus RSS. Now, another concept, our major focus was goodness of fit. Let us now define goodness of fit. Our total variation was summation yi minus y bar whole square. Out of this total variation, how much I am able to explain? yi hat minus y bar. Now, if I take a percentage of total variation in yi, that is explained by the model, which is yi hat minus y bar, a proportion of this with respect to the total variation, a proportion of ESS with respect to total sum of square TSS is actually the goodness of fit. Okay? More is the ESS, better is your. That means what I am saying, let us take a proportion ESS by TSS. Out of total variation, how much your model is going to explain? This proportion is known as R square or goodness of fit measure. Okay? R square or goodness of fit measure. That means R square basically says, so if the R square is, let us say 0.5090 in our example, what does it mean? It means 50.90 percentage of total variation in yi in consumption is actually explained by your model. That is the meaning of R square. That means ESS by TSS ratio is 0.5090, that you have to understand. The ratio of ESS and TSS out of the total variation in yi, which is yi minus y bar whole square, how much your model is going to explain, that proportion is known as R square. It means that my model is going to explain 50.90 percentage of total variation in yi around its mean value. Okay. So, now we have learned the three sum of square TSS, ESS and RSS, and we will now go back to Stata and we will see how Stata has reported those. Now, see, look at here, they are source, they are this table, this particular table, here you see the R square, R square is not 0.5090, I have written wrong. This R square is, what is the value? R square is actually 0.9621, 0.9621. So, that means 96.21% variation in y is actually explained by your model, which is really good, R square 0.9621, and you have to keep in mind that R square lies between, this is the limit, So, when r square is actually 1, so that means we can write these two cases, Case 1, let us say r square equals to 1, that means your yi hat is actually your yi. So, this point is actually whatever your model predicted and whatever your actual y, that is same. So, that means your model can perfectly predict someone consumption. That is a theoretical possibility. So, it is not possible to estimate a model for which yi hat equals to yi. Your prediction and observe, there is no deviation. It is a theoretical possibility. So, when r square equals to 1 means this is the meaning yi hat equals to yi. Similarly, what does then r square equals to 0 mean? When r square equals to 0, that means your model is not able to explain anything. Now, you in terms of the diagram, that means there is no explain sum of square, you are not able to explain anything, that is why it is 0. So, obviously, your line will then tend towards downwards and it will converge to the average line. So, that means your yi hat is actually your y bar. So, that means this regression line will tend downward and it will converge to the average line. So, that means the average value of yi is the best prediction for this model, since I do not have any, my explanatory variable does not have any explanatory power. Anyway, these are the two extreme possible cases, theoretical possibility. In reality, we do not get r square equal to 0 or 1, rather r square will always lie between 0 and 1. Now, here what you do, now this table, if you look at this table where they have mentioned source and then there are two model, residual and total, and then you see this particular table is called Anova table. What is it called? Anova. Anova means analysis of variance. So, Anova table, this TSS, ESS and RSS what Stata is giving, this is called Anova table, A-N-O-V-A. This is called analysis of variance. Analysis of variance. See, this diagram is also a diagrammetric representation of Anova only. This is my total sum of square, total variation in y. Out of this I am able to explain this. That is why this is called my this is called my ESS, and this is called RSS, and this is TSS. So, this diagram also shows the analysis of variance only, or Anova. Now, what is ESS here? The term what we have written ESS, in Stata's language it is called model sum of square. So, ESS in Stata is known as model sum of square, that is why Stata has given, look, this is model. So, your model is able to explain how much, and the ESS model sum of explained sum of square value is 8552.77. 8552.77 is the model sum of square. And what is the residual sum of square? Residual sum of square is 33.27, and if you add these two, then the total sum of square is 8890. 8890. So, this is called analysis of variance, which we have understood using the simple diagram, right, simple diagram. Then they have also given degrees of freedom, degrees of freedom. Now, degrees of freedom is something How do you know the degrees of freedom? For any particular measure, for example, let us say I am trying to understand the degrees of freedom for this summation yi minus y bar whole square I running from 1 to n. I am trying to understand the degrees of freedom here. And how do you define degrees of freedom? Number of restriction imposed okay, sorry, I will write total number of observation, total number of observation minus number of linear restriction. That is how the degrees of freedom concept is defined. See here, what is my total number of observation? Look, it is I running from 1 to n. That means I have n number of observation. And out of n number of observation, how many restriction I have put? I have given only one restriction in terms of y bar. Then degrees of freedom for this is defined as n minus 1. Why this is so? That means one observation is lost due to the restriction imposed. That is why n minus 1 number of observations are able to move freely to define this particular measure. That is the concept of degrees of freedom. What is the degrees of freedom? For a particular measure is defined as total number of observations minus number of linear restriction. Here total number of observation is n and number of restriction is 1, that is why it is degrees of freedom is n minus 1. Okay. Similarly, if you try to understand the degrees of freedom for RSS, now RSS how we have defined? It is defined as yi minus yi hat whole square I running from 1 to n. That means from here what I can understand that to compute RSS, it is necessary to compute yi hat, and to compute yi hat, we need to compute alpha hat and beta hat, right. That means if you have n number of total observations, while estimating alpha hat and beta hat, you will lose 2 observation, and that is why degrees of freedom for RSS would be n minus 2, where 2 is the total number of parameters to be estimated. Now in this model you have only 2 parameters. That means when you have only one explanatory variable, you have 2 parameters to be estimated. For a generalized model, let us say I am doing yi equals to alpha plus beta 1 x1 I plus beta 2 x2 I plus beta k x k I plus ui. Here I am trying to estimate actually k number of parameters. Okay. So that is the reason I would say that when you have k number of parameters, then degrees of freedom for RSS would be n minus k for a generalized model. Okay. All right. So, that means n minus k is the degrees of freedom. Then what should be the degrees of freedom for ESS? Degrees of freedom for ESS would be df for TSS minus df for RSS, right. So, that means in this case, in a 2 variable model, it would be n minus 1 minus n minus 2. So, that means 1. This is how you can calculate the degrees of freedom, and for a general model, then it would become n minus 1. So, this would become n minus 1 minus n minus k. So, it would become k degrees of freedom for TSS, right. Now, you see in Stata total number of observation is 10, that is why degrees of freedom for TSS total sum of square is n minus 1 9. And what is the degrees of freedom for RSS? Since I have only one explanatory variable, that means 2 parameters I am estimating. So, 10 minus 2, which is 8, and 9 minus 8 equals to 1. That is why it is called, that is how we can calculate the degrees of freedom for TSS, RSS and ESS. So, first we will calculate the degrees of freedom for TSS, which is always n minus 1, and the degrees of freedom for RSS is actually n minus k for the generalized model, and in this case it is n minus 2. Once you know the degrees of freedom for TSS, degrees of freedom for RSS, just take the difference between these two, you will get the degrees of freedom for your ESS model sum of square. And then Stata has also defined as MS, mean sum of square, which is nothing but the SS divided by E, degrees of freedom. So, if you divide this, 8550.72 divided by 1 is this. Similarly, if you divide this by 8, it will come 42.15. So, it is simply SS by its degrees of freedom. And if you take the ratio of these two MS, then that will lead to another important statistic, which is called F statistic. Okay. MS of model, MS of residual, if you take, then that will give you a statistic which is called F, and that value will turn out to be 202. What is the implication of that F statistic? That we will discuss later once you understand the hypothesis testing, right. So, with this we are just closing our discussion on today. So, today we discussed about the meaning of regression, what are the 3 important properties of beta hat that we estimate. Then we have also learned how to estimate the model, how to interpret the coefficient, and then we have also learned the goodness of fit measure, and using a simple diagram we understand the analysis of variance, 3 important components that is there in the analysis of variance, total sum of square, which you are going to explain through your model defined as sum of yi minus y bar whole square, and then the other 2 components is explain sum of square, and in Stata it is actually model sum of square, and then the residual sum of square. Okay. And we have also learned how to interpret the Anova from the diagram to this table what Stata is reporting. Now, in our next class we will try to understand the interval estimation portion, that means the hypothesis testing, to ensure that this 0.50 what I get here, that is not out of a chance, rather it is statistically different from 0. Okay. So, in our next class we will discuss about hypothesis testing.